Hello, everyone.
Hello.
Hi, how you doing? So I'm signed out. Let's see. Can you all see my screen?
Yes.
All right. Just do a quick run. Just making checking the speed here. Oh yeah, that's much better. All right. All right, everybody still there? Lose anybody? Hello?
I'm still here.
Okay,
Yeah, we
good.
can still hear you.
Yeah, I switched Wi-Fi spots, so I was wondering if I had lost anybody. All right, just give everybody a couple more minutes. Okay. All right. All right, welcome everyone. Let's see, let's take a look at the syllabus, see where we are, where we've been and where we're going. Let's see. Right, so we're finishing up week number 10. We will keep discussing indexing and also start talking about transactions. Also, we did talk about the next assignment DB9, which won't be due until a week from today. So we discussed that and we demoed that in our last lecture, and we'll keep discussing that today and perhaps spill over till next week. Next week we will be talking about another type of database, a non-relational database. All this semester we've been talking about relational databases, but there's a whole new additional world out there about other types of databases that are available, in particular non-relational databases for real-time systems, non-structured databases that address a completely different set of issues. And we'll talk about that next week. Also, the P1 is approaching and so I created an assignment for you, although it's not due for another 2.5 weeks. We do want to start preparing for working for the project, and so I'd like to discuss that at least for a little bit today, and plan for that. That's it's coming up those last 2 or 3 weeks that we're going to be discussing about projects and working towards that. So first of all, we do need to create groups of students, and although some students have gone ahead and created their own groups, their own student groups. I see that only 4 groups have been created so far, and so what I did is that I created these groups that you can join, and I see that some folks have already joined, and you can see the groups by going to people here on the left hand side, and then clicking on the database design groups, right? And then you can join any of these groups down here. Okay, the groups can be as small as 1 person per group, or as big as 4 folks per group. Okay, even if you are going to be working all by yourself, please join a group, since the assignment will only be visible to folks who have joined a group. So if you don't join a group, I don't believe you can submit, or we won't be able to grade you if you don't join a group. Join a group that what I suggest is one in the team member. A team member in the group can see a group that is not taken, and then join that group, kind of like to claim that group, right? Join the group, and just to make sure that you don't have 2 people from different groups joining the same group. So once that person has claimed that group, they can tell the rest of the team members to join, group number 13 or something, or whatever. And so that everybody falls into the right group. I'm not sure if you can leave a group and join another group. I think for that you'll need either my assistance or the TA's assistance, and just let us know if you're having any trouble joining or leaving or whatever, and the TAs and myself will help you out. All right, so let us know. And whenever you submit anything for the project, it's a team effort, right? So there's only one thing that needs to be submitted, right? If you're 4, just one submission is enough for that group, right? And at the end of the semester, everybody's going to get the same grade that is in the group. So I tend to prefer smaller groups. Bigger groups tend to be harder to manage. Oftentimes, unfortunately, you find that in big groups you find one person that it's not pulling their weight, and the other team members at the end of the semester start complaining, and it just makes it so much inconvenient and much uncomfortable for everybody. So please just be aware of that, and just keep an eye on making sure that everybody is helping out in the group. So for the first project related assignment, according to the syllabus, we're gonna be talking about more in detail about a week from now. Well, no, on Tuesday. Yeah, we'll talk about it in more detail. April 6th. So a week from Tuesday, we'll talk about it in more detail. But I just wanted to make you aware of it. You can start working this right away. You don't have to wait until this goes out. It's already available. I would encourage you to get started. Perhaps one person in the group, you can divvy up the work amongst 4 of you and start working on it. And this first P1, which won't be due till mid-April, it's asking you to create a UML diagram of whatever it is that you as a team are going to be building, and then and actually create a database, right? Using SQL, create statements, create the relational data model, right? A couple of several tables, relationships, and fill it up with dummy data, some sample data, and then export that database and then submit that database. So you'll be submitting two things. One is a UML diagram as a PDF or Word document. It could be a link to a document that is online, or you can upload a PDF document. So that's one thing. And the other one is the database implementation. The actual, you're gonna build a couple of tables. You're gonna create your foreign keys, primary keys, relationships, right? And you're gonna populate it with sample data, and then you're gonna export that, right? And as you remember, when you export, you get several files that create the tables, that populate the tables, and then you're gonna zip that up, and you're going to submit that your export, right, of your database. So that's P1. Again, this is due mid-April, but I would not wait till mid-April. I would get started on this right away. Meet with your team members and maybe divvy up the work. Maybe you can work together. Perhaps half of you is working on the UML diagram while the other one is building the database, and just work together. The UML diagram and the database it can evolve if you decide later on to add another table or remove a table or change some data types. That's fine. This data model is a preliminary design. And also the implementation is also preliminary. If you need to change it because you discover something a week later, that's totally fine, right? So this doesn't need to be the absolute latest design or latest implementation. You're welcome to change it as you work your way through this. Okay, this is mostly for you, right? This design and this implementation is mostly for you. So we're going to have very little to say. This is mostly for your own working towards implementing something that works, right? Something that you can interact with and actually add data, and so that's what we're going to be looking at the end. So design the data model, implement the database. It needs to meet the following requirements. Whatever it is that you build needs to meet the following requirements. Okay, and these are all minimal requirements, and this is available as a hyperlink inside of P1. Okay, so data model, design a normalized database that meets the requirements discussed in class, which we are discussing right now. So this link opens up the requirements. Here they are. It says the final project is a chance to work as a part of a small team, blah, blah, blah. So it asks you to create a UML diagram, right? And the UML diagram should have class names, properties, data types, relationships, cardinality. So, the full-blown data model. You need to reify the classes, right, with the intention that you are going to be implementing this in a relational database. So, make sure that if you have many relationships, you don't leave it as just star, right? Convert that into either a mapping table or an association. So with the intention that you are going to implement it in a relational database. Okay. You should have your data model. Your data model should have at least one user or one type of user, right? It could be a faculty, it could be a student, it could be a cook. Okay, it could be a sports fan. It could be whatever you choose, right? Whatever domain you choose. And when I say domain, I mean some kind of topic. Choose a topic, whatever topic you choose, whether it's food, sports, right, finance, whatever you choose, education. So choose a topic. I call it domain. Choose a domain, right, and then decide a user that would inhabit that domain. Okay, now that user, you can have more type of users, but at least one. Okay, whatever it is, stockbroker, restaurant owner, right? Whatever. That user should have at least the following fields. They should have a first name, last name, username, password, email, and date of birth. So at least those fields, okay? And you're free to add more. Okay, you're welcome to add anything else. Then domain object data model. Again, by domain, I mean, some topic of interest of yours, right? A domain could be movies, could be travel, right? Could be food, whatever topic or domain you want to choose. So within that domain, choose at least 2 objects or 2 types of objects, right, in that topic or in that domain. So for instance, if you choose the domain movies, then a domain object is something that would inhabit that topic or that domain, right? So a movie is in the topic movie, or theaters, right? Or a review of a movie. That's also a domain object, right? So things that exist, that only exist in that domain, in that topic, right? So for instance, if you choose a domain or the topic food, then nouns that would exist in the food realm would be recipes or ingredients or nutritional information. So those are all classes or objects, right, that would exist in the world of food. Right? If you choose travel as your domain, right, then a domain object might be a plane ticket or a reservation or a hotel or airlines. Those are all valid objects within the topic or the domain of travel. That makes sense? All right, so one user or one type of user and at least 2 domain objects. Then you need to implement some kind of relationships, right? And the relationship, you can choose to be one-to-many or a many-to-many. And so you have to have at least one domain object to domain object relationship. Okay, so the 2 domain objects that you chose, they somehow need to be related to one another somehow. Okay, if you have theaters and you have movies, well, movies are playing in theaters. So if you choose a theater, you can have a list of all the movies that are playing in that theater. Those are domain objects that are somehow related to one another, right? And the relationship between theaters and movies, it's whatever you want it to be, right? It could be a one-to-many relationship, it could be a many-to-many relationship. You choose, right? You're free to choose whatever you want. If your domain was music, then a domain object might be songs or playlists. Again, a playlist might contain many songs. Yes. If the domain was okay, you understand, right? You also need to have at least one user to domain object relationship. So this is a human user related to some object, right? So for instance, if you have an actor, right? An actor can, as a user, as a human being, can act in many movies, right? So a domain object is a movie, a non-human, and then the actor, which is a human, and they're related, right? An actor can act in many movies, okay, or an actor can win many awards, okay, or an actor can have many nominations, okay. So they're related, either one-to-many relationship or many-to-many. Again, you're free to choose whether it's one-to-many or many-to-many. It's your choice. Okay. Also, you should have at least one portable enumeration. Portable enumeration, if you remember, a portable enumeration is, right, when you can say that something is a particular category, right? So for instance, a user might have many roles, right? So me as a user, I could have the role of a faculty, of a student, as a staff, right? So there should be a table, right, that is called maybe roles, that lists all the possible roles, and those should be primary keys. And then the user would have a foreign key to the roles table, right, would have a field called roles or role, right, who's a foreign key that goes to the roles table, right? And you can perhaps choose from some drop down for the role of that user. Or same, a semester can have different quarters, right? A semester could be fall, spring, summer, summer 1, summer 2. Or a movie can be many genres, right? It could be horror, comedy, drama, sci-fi. So those are all enumerated data types. And we saw how to implement that, right? In our example of in the homework, we were using blogs, right? And blogs could be, posts could be different topics, right? Could be space, cars, and we saw how to implement that. So follow that lead. Okay, so you need also to implement some kind of user interface to interact with whatever database you choose to build. And you should have at least the following screens, right? For each user type or for each domain object type, there should be at least 2 screens, right? So if you have a student object, then you should have at least one way of listing or displaying a list of students, and you should have a screen that allows you to edit that user or that student. If you have courses, so if student is your user domain, user object, and courses and sections are your domain objects, then you would end up with 6 screens. 2 for the student, 2 for the course, and 2 for the section. Right? One of them, lists the content. The other one allows you to edit a particular record. Okay. The twist here is that some of these have relationships with one another, right? So a course, for instance, a course might have many sections, right? So sections, the screen, the section screen can either list all the sections, or more interestingly, right, you would display only a subset of the sections, right? Only the sections that belong to a particular course, right? So you would see the course, and then you'd be able to see the lessons for the sections for that course, right? Or if I use students, right, because a student can be enrolled in many sections, I like to see what sections is a particular student enrolled in, or vice versa. Starting from a section, I would like to be able to see the list of students that are enrolled in a particular section. That makes sense? So the student list can be used for many things. It could be used for displaying a list of all the students, or it could be used also for displaying the students for a given section, right? So if you give me the section, I'll display the students in that section. Same thing for where courses can exist on their own, right? Because nobody's the parent of a course, right? But from a particular course, I should be able to display all the sections for that course, right? So section list is used for displaying all the sections, or displaying the sections for a given student, or displaying the sections for a given course. Okay, and all the editors are either for editing a particular record or creating a brand new record, like we showed you how to do in the prototype code that I gave you, right? That you are currently working on, DB7, DB8, and whatnot. Okay. All right. So yeah, there you go. So that's those are the requirements for the project. Let's see. Any questions? Everybody can still hear me, yes?
Yep.
Okay, great. All right, excellent. So so if there are no questions, I'll jump to today's lecture. We're going to keep discussing transactions and talk about indexing and finish that up. Let's see. I think Ryan is.
Yeah, I just posted one in chat, but I can ask it. So, Can we use NoSQL for this, or is it just this?
Actually, yes, yes, you could use NoSQL. Even though here I'm saying relational database, you can actually use NoSQL.
Okay, thanks.
I'll I'll um I'll note that on the as part of the requirements. Yes, you can use NoSQL. Let's see. I think there's a couple more questions on the chat. Let me take a look at this. Canvas due dates for the homeworks have not been updated. Ooh, okay. I'll do that. Are these groups for people in this section specifically? Yes, these groups are for this section specifically. If if you want to have students that are in different sections and you want to work together, well, join separate groups in the different sections. At the end of the semester, we're going to ask you, you're going to fill out a form. I'm going to ask you, what group you belong to. And if it's cross section, then you'll need to tell me, well, what group do you belong to in the other section? Okay, so that we'll know that both sections, both groups in different sections are going to get the same grade. So that'll be at the end of the semester. We'll ask you, what section you're in, and just one of them just one group needs to submit. That's all, right? You don't have to submit it in both sections. And we'll figure it out when we'll know which students are in what group and which ones are cross section. I am in the 3 but attending. Yeah, we're treating both sections as if it were one big section. So yes, you can go across sections. How should we create groups if we have gotten approval to work across sections? Yeah, I just explained that. Can our final probably be non-SQL? Yes. Our group size is 2 to 4. It could be as small as 1 person or up to 4 persons. Do we need to make a web app? No, you can make any application you want. I know that there's one team is making a mobile application, with the phone, which is pretty cool. It could be a desktop applications if you feel comfortable using some other user interface library, then by all means. Okay. Oops, I didn't want to do that. Leave the chat open. For homework 7 and 8, will we lose points if we have bug? No, I fully expect everybody to get full credit for assignments 7 and 8. Again, the 7 and 8 are mostly just to get you going, to give you some tools to get you going for the project. You can totally use it for your own purposes, for building the application for the final project. But my intention is that we're going to help you go through and implement the whole assignment and help you all the way through to be successful in these two assignments. I mean, the only way that you could not get full credit is that you completely blew it away and just didn't do anything. Okay. But yes, make every effort to get that up and running, and please reach out to me and TAs. We're all running extra office hours to help you out and be successful in those 2 assignments. All right, let's focus on today's business. Okay. Okay, so we had talked about indexing. Let's finish that up a little bit further. Let's see. Okay, so we had talked about indexing and that not always was always a good idea. And we said that to be able to measure whether it was a good idea to use indexes or not was to understand first what it is that we were trying to optimize, right? And we discussed that really we're not trying to optimize the number of comparisons like we would if these were algorithms, right? In algorithms, typically we look at we have to define what it is that we're trying to minimize or maximize, and oftentimes you're maximizing or minimizing space or time. Here we're trying to minimize the time, the amount of times that we go out to the disk, since reading from the file system is several orders of magnitude slower than running an algorithm to compare or do something like that. So that's what we want to optimize, right? And so we started looking at examples with real life numbers of querying a database with 40,000 students, 40 departments, with an average of 1,000 students per department, and having a file size that can contain 10 records. And we saw that if you were retrieving data with a unique index, right, on the primary key, for instance, then you would get huge amounts of improvement in performance, since if you compare the time that it takes to do a full scan, it's 4,000 reads to the file system, whereas it would only take 3, 4, 5 reads to go out and use indices, right, and traverse the either the hash or traverse the tree, right, down to the leaf, and then with the record identifier jump to where the record actually is. Right, we saw that if you're doing a single record retrieval by its key, right, you would get thousands of improvements in performance. But not so if you were using a non-unique key, such as major ID, where each record identifier might actually point to multiple records in the original table. Okay, we saw that that in that case, because you have an average of 1,000 students per major, so major ID 20. If you have major ID 20, that would mean that there would be 1,000 students with major ID 20. So you would end up doing 1,000 times, right, the individual query for an individual record, right? So you would end up doing 1,000 queries to the file system. So in that case, right, the comparison among doing a full scan and doing and using indices, we see that the improvement is not that much. It's still 4 times faster, right? But it's not thousands of times faster like it was when you're using unique identifier, unique indices. Okay, and the reason is that when you read 10 items per block, oftentimes some of those items might be in some of the items that you care about that are in major ID 20, might have been in those 10 records that you read into memory. But because you're not doing a scan, right, those additional records that might have been there, you don't know about, right? You throw away the blocks, and you have to do it a second read to retrieve that unique that record again that you had read it already, right? So there are some inefficiencies that would have been solved if you would have done a scan. Now, but here's an edge case, right? Here's an edge case where indices actually might work against you, right? We saw that if you're using non-unique indices like major ID, we see that the number of reads that go out to the server, that go out to the database, right, it's actually proportional, right, to the number of records that each non-unique identifier is mapped to, right? So that's why over here, right, it was 1,000 reads. The reason it's 1,000 reads is that for each major ID foreign key, there could be 1,000 of them, right? So you would have to make 1,000 reads, right? So well, what if the numbers change a little bit? Instead of having 40 departments that we had before, right? If we had 40 departments and you have 40,000 students, then that's about 1,000 students per department. But what if you only had 8 departments? Well, if you had 8 departments, then that means that there's 5,000 students, right? 5,000 students per department. That would mean that, because this is not unique and not a unique index, you would be making 5,000 reads, 5,000 reads to retrieve the 5,000 students that are in a particular department. That would mean that it would take you longer, right? It would be worse, right, if you were using indices, because if you're doing a full scan, it would only take you 4,000 reads. But because now the non-unique index is referencing 5,000 records, individually, you're going to have to read them all individually, and that's going to be 5,000 reads. So it's actually worse, right? So it's actually faster to do a full scan of the database than to use the index to retrieve individual records. Okay. All right. So let's talk about composite indices. So up to this point, we've talked about an individual index either being either a unique index or an individual index being a non-unique index, right? But you can combine these. You can combine fields and say that my index is actually the combination of 2 other fields. Okay, so your index is actually the composite of these 2. And the way the database uses this idea, right, is that it will concatenate the values of these fields, and that value, right, needs to be unique and will be used to build the tree, right? And so the tree or the hash will be built based on that on the concatenation of 2 fields, and that's what drives either going left or right in the tree, right, or as an index in a hash table, right? Now we need to understand how this works, because depending on the query that you're going to be using, these index might be useful to you or might be useless to you, right? So for instance, say you choose as an index, you choose these 2 fields, model and year. So what that means is that I'm going to take the values of those fields, model and year, I'm going to concatenate them, and the resulting value is going to be my index. Okay, so for instance, and then I'm going to sort and I'm going to organize my table based on the values of concatenating. So for instance, here's model year, and we chose that order, the model concatenated with the year, and then sort the resulting values, right? Or organize the tree, the B tree, based on that, on the concatenation of these values. So, if you sort it, then it becomes Corolla, Corolla, Grand Cherokee, Odyssey, and so on and so forth. Odyssey. Notice that it's alphabetically ordered, right? Now we could have instead chosen to the opposite, go to year model instead of model year. So that means now that the concatenation of the values is backwards, right? It's 2004 Corolla, 2006 Corolla, 2008 Odyssey, right? And then sort by the resulting concatenation. Okay. Now, depending on the select statement that you're going to be using, it might have been better to go one way or going the other way, right? So order does matter. So for instance, if your query, says something like, select star from, my card, blah, 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 where, right? And you have a year equal 2004 and year equal Odyssey. Well, it doesn't really matter which choice you would have chosen, either model year or year model as your composite. The database is going to take your values, and then it's going to concatenate them. And then use the resulting concatenation to look up the sorted keys, using the resulting concatenation, right? And it'll remember what it used to concatenate, right? For instance, it'll remember that it was model year. So what it'll do is that it'll concatenate Odyssey, and then it'll put 2004, and we'll use that to look up your key. right? Or if you would have chosen year model, then you would have done that instead, right? It'll take 2004 and concatenate Odyssey at the end, and then use that to look up, right? Look up in your table, right? In your tree or your hash table. Yes, but if your where clause, right? If your where clause only uses part of the key, right? Where it uses, where the year equals something, but there's no and, right? There's no and, then now it does matter if you have chosen the composite key to be model year as opposed to year model. If you would have chosen year model, well, since it's already sorted by year, right? Notice that year is at the beginning, then 2004 is great. I could find real quick where that is, right? I can look at and find these two, and then say, okay, well, which one is it? One or the other? I can return both. Okay, but that's great because it's sorted already by that. But if you would have chosen model year, then this left-hand side it's useless to me, right? Because as far as the year is concerned, it's random, right? It's not necessarily ordered. I could have 2011 at the beginning or at the end, right? And it means nothing, right? It's because it's sorted by the model, not the year, right? And vice versa, right? If your query is a where model equal Odyssey, then the left-hand side would have been better, but not the right-hand side. Now, oftentimes we have the question, to index or not to index, and oftentimes folks make the wrong have the wrong impression that indexing is always good. Okay, and so well, but it's obviously, like somebody said, there are no solutions, there are only compromises. Okay, so yeah, there's no one solution fits all. It depends what you're doing. Okay, and first of all, it could be really, really expensive to maintain indices, and so your product table could be several gigabytes, right? And then all the indices that you're going to have, right, are going to be additional storage that you're going to need. Depending on the indices, oftentimes the index table will be a smaller version, maybe half the size, a quarter of the size of the original table. Okay, but nevertheless, it could take space. You can have, each index could be several gigabytes big, right? It's a smaller version, but still it's data, right? And so for every index, well, that's an additional cost. Now, somebody might say, well, memory's cheap. Who cares, right? But this could definitely grow into fairly sizable chunks, right? That might be hard to manage because usually you're not, in an enterprise application, right, with big corporations and whatnot, you're not talking about one database. You're talking about lots of databases, and then each database might have multiple versions, right? The one that it's in production, right? The one that all your customers are going out to have this production database. Usually that database is you keep a copy of it for disaster recovery. If the zombie apocalypse comes, well, maybe we can't do much. The production database goes down, and you want to keep a copy of it. Usually there are many environments where developers are developing, and they have copies of the database, right, so that they can actually do their work. Right? Oftentimes they have multiple development environments, right, with where you obfuscate credit card numbers, or you obfuscate social security numbers, or real names. You also usually when you go through the different development process, right, you also have a user acceptance testing where you deploy to a system where you have all the quality assurance engineers check to see if everything's okay, right? So there's different versions of the same database, each one with their own indices that have to be recreated, blah, blah, blah. There's usually another database for performance testing, right? Making sure that, it can sustain, thousands of users hitting it at the same time, and you do all that kind of testing there. Also, right, the improvements in performance that you get from potential improvements in performance you get from reading the data, right? You pay that cost at doing other operations, right? So, if you were able at first to insert, right, records into a database, when you start adding indices, insert becomes much slower, right? We saw that in the assignment, right? We demonstrated that in the assignment, right? That the tables that did not have indices were much faster when we inserted into the database, right? And it was much slower when it had indices, right? So, for instance, if you were able to insert 100 records into a table per second, that had no indices, when you start adding indices, that performance goes down to 65, and if you add 2 indices, it goes down to 22, and then 15 or 5. As you add more and more indices, it gets much slower to insert data into the database, right? So again, you have to make sure that what are you using the table for, right? Does the table have mostly read operations from that table? Are you writing a lot to that table, right? You have to look at your queries, right? If your queries are mostly individual queries on individual records, then definitely indexing is going to work in your favor. But if your queries come back with lots of huge result sets, okay, that are very, very commonly coming back with with 20, 30, 40% of the results in the table, then that's not going to do much for you, right? It might be as quicker to just go and do a full scan with no indices. So it depends, right? So you have to consider all these things before you blanketly or blindly accept going with indices. Okay. All right. So let's talk about transactions. Let's introduce the topic. Let's see. Any questions? If anybody's raising their hand. Oops. Where did it go? Where did the chat go? I lost the chat. Where'd the chat go? Oh, there it is. Yep. Paste questions on the chat. I don't think there's any more questions. Okay. All right. So let's keep going. Let's talk about transactions. Okay, so transactions is going to allow us to deal with concurrent access to the database, right? It is very seldom that we will be the only ones accessing our database. Very much, I mean, up to this point, you have been indeed the only ones who have been using your database. It's just you and doing some queries and whatnot. But when you put it in production, usually it'll be dozens, hundreds, thousands of folks using the database concurrently, right? Each one with their own login information, right? And so how do you deal with multiple access to the database, right? Now, usually these accesses are represented programmatically as different processes or multiple threads that are running simultaneously in the CPU, right? And that are or making multiple connections simultaneously to the database, each one with their own login, right? And so they all want to. Many times they're going to be accessing the same piece of information. Just imagine, just you going out to, make a reservation in an airline or for a restaurant or for a movie, right? Usually you're not the only one who is looking at whether a seat on an airline, right, is available or not, right? Is it free or not? And so, what if everybody's looking at the same piece of information and you see that all these seats are available, and not only you, but so could be another 100 people looking at the same information. So how do you reconcile when multiple folks are looking at the same information, making a decision based on what they see, right? And is it the correct decision? Or what they're looking at stale information that can drive them to make the wrong decision, right? So transactions allows us to deal with all these challenges. Okay, so here graphically we have an example here in a users table, and you have a particular user ID, and that person's age is 20 years old. And so here you have 4 processes, are working on the same exact record, right? One of them is reading the record saying, give me the user where the ID of that user is 1. So they might read that person, right, age is 20. But then you have another process here who's trying to update the same record, and it's trying to change the person's age to be 21. So right there, you might say, well, what does process 1 see? Do they see that the age is 20 or 21? Should I let this person drink or not drink? Right, here in the US, anyway. And you have a couple other processes that are one is trying to delete the record, right? So wait a minute. So I'm trying to update a record that somebody is going to remove it. Okay, so now you have this kind of like race condition of saying, well, which one wins, right? Is it last one standing? Okay, this one's trying to insert another user with 21 years old, right? So which one is it? So transaction is going to allow us to deal with this mess, okay? So transactions allows us to isolate all these folks, right, that are working with the data that they want to concurrently come in here and deal with the same piece of information. Transactions are going to allow us to isolate them so that they can work independently of each other, okay? In particular, for instance, if I'm looking at seats on an airplane, and the only way that the airline can actually guarantee that what I'm looking at is reality, right? The only way that they can guarantee it is that I am the only one looking at this information, and everybody else is locked out, right? And until I don't make a decision, right, the seats are frozen. Nobody can make a change. Okay, so transactions allow us to do that. Allow us to to make a lock and decide, right? Well, you're holding the lock until you don't release the lock, right? Nobody else can make any changes, right? So transactions can deal with that. Now, that goes against other things that we'd like to be able to do, right? Right? Because imagine a person is taking, I don't know, 2, 3, 4, 5 minutes to make a decision on whether they want the seat or not. And you have hundreds of other folks that kind of like waiting for this person to make a decision. So we have to weigh what, these two competing things, right? We don't want to have folks waiting on each other, but we want folks to be working with real data, right? And making a correct decision. So how do you weigh those two things, right? How do you weigh that we want to maintain the multiple users at the same time, but how is it that we can, folks look at real data? So other things, right, is that what if we, how is it that we want to deal with other cases where, for me to make a decision, there might be several things that depend on my decision, right? I'm sorry, my decision is dependent on several things happening, right? So for instance, one table might hold information about hotels, another one about cars, another one about airlines, right? And as far as I'm concerned, right, for me, traveling to go visit my daughter, right, I might need all three things to happen. I might need to be able to book a car, an airplane ticket, and a room to stay at a hotel, right? So for me, traveling, it includes all those three things, even though folks might consider them to be individual things, right? One thing is to get a car, one thing is to get a hotel, one thing is to get a ticket to travel there, right? Even though folks might consider those to be individual unto themselves, I see it as one big thing, right? As those three things need to occur, right? If I have a plane ticket to go, but I don't have a place to stay, right, and I have a car, then I'm not going, right, because I don't have a place to sleep, right? Or if I have a place to stay, I have a ticket, but I don't have a car, then that doesn't work for me either, right? So transactions allow us to group together things that, they all happen or none of them happen, right? So transactions allow us to make sure that we have a lock or guarantee from everybody, and that if it doesn't happen, right, I can always go back and say, oh, forget it, just return everything, right? So yeah, so definitely, transactions are going to allow us to, if we see failures, transaction is going to allow us to recover from those failures, right? If we see some inconsistency in the data because things happen in the wrong order, or things that were not supposed to happen did happen, transaction is going to leave a breadcrumb, right? So that we can always backtrack to the previous state of the database where there was a consistent state. Okay, so it allows us to identify inconsistent states and roll back the database to a previously consistent state, right? It allows us to isolate processes that are running concurrently, trying to access data. We say that transactions provides the following features, right? It allows databases to be ACID, we say, right? So ACID is an acronym that stands for atomic. So databases can be atomic, they can be consistent, isolated, and durable. Okay, and by atomic, we mean that we can group together actions that either all happen or none of them happen, right? Group things together logically. And consistent, where we can always make sure that guarantee that the database is always going to be in a consistent state. That if we find the database to be in an inconsistent state, we can always backtrack to a previously consistent state, right? Safely. Isolation, where you may have multiple processes running at the same time, and you can establish different policies of what it is that we're going to allow folks to do concurrently and what things that we're not going to allow to do concurrently. And durable, right? If we make a change today, we can guarantee that those changes will go into the future, right? If we lose power or whatever, right? We can come back tomorrow, we plug it in, and the data is still there, right? So those are features of transactions. Now, transactions allow us to manipulate or manage the life cycle of the data, right? Of how data evolves over time through the use of what are called transaction commits and rollbacks, right? And we demonstrated this in our earlier lecture, right? Where we can start a transaction, and then those any changes we make inside of a transaction are temporary, and no one sees our changes until we commit those changes so that others can see them, or we can just throw it away by rolling back those changes so nobody can see them. Okay. So first, let's see what are the problems that transactions are trying to solve, right? So there's a broad category of things that could happen if we didn't have transactions, right? If we let it alone and just live without transactions, what could go wrong, right? And then we'll see how transactions can deal with each one of these issues. Okay, so these are the most common problems that occur when you don't have transactions. One of them is called a dirty read. All right, so a dirty read means that somebody's in the process of changing something, right? And the data that you're looking at, right, is stale. Okay, very much like I go to my website where I can see the seats in an airplane, and I read the database, and the database shows me that seat number 10A is available. But meanwhile, unbeknownst to me, right, while I'm looking at this in my screen, and I'm trying to make a decision if I want seat 10A, behind the scenes, other people are dealing with the database, and they are updating the state of the database, right? And seat 10A is no longer available, even though my user interface is saying that it is indeed available, right? So what I'm doing here is that I'm looking at a piece of data that is already stale, right? And so we call that a dirty read, right? That somebody might be changing something and they haven't yet finished, right? They were in the middle of changing, and they inadvertently or in their logic of execution, they made the seat available. I read the data, and now my user interface says that it's available, right? But in the logic, they were in the middle of changing the state. They weren't done. It hadn't settled yet, right? And actually, the result was going to be that it was going to be unavailable, right? So I'm looking at data that was temporary or intransient, right? That was not yet settled. So we call that dirty reads, right? And we'll see how transactions can deal with that. The other similar example is called a non-repeatable read, right? That I make a read, I read from the database, I have that data. It's kind of similar to what we just described. I guess I described both of them. Non-repeatable read means that I go to the database and I see a value, and then I make an assumption. My assumption is that what I read is not going to change on me, right? My logic in my code assumes that when I read that data from the database, I'm assuming that the copy that I have in memory is not going to change in the database, right? But it actually, right, my assumption might be wrong. Somebody's texting me. What? Wait a minute. Okay. So if my assumption is wrong, right? When I read back from the database, it turns out that it had changed, right? So my entire assumption in my code might lead my code to make wrong decisions. Then there's phantom reads. Phantom reads is another example of I make not an individual record, but I do a select statement that comes back with many records. It comes back with 10 records. Yes, select star from products that are less than $10, whatever, right? And it comes back with 1,000 products that are less than $10, right? But at the same time that I was doing that, concurrently, somebody might be inserting a record or removing a record, right? Or one of the rows by which I would have seen instead of 1,000 records, I might have seen maybe 1,001 or 999 records, right? So the 1,000 records that I see are actually stale now, right? Because if I would have waited a little bit, I would have seen that extra record, right? Or if I would have done it fast enough, I would not have seen that record. Okay, so we call those phantom reads. Okay, and transaction is going to help us deal with all these challenges. Okay, these are the problems that we might run into. So how do the databases deal with this? So the databases deal with these challenges using these 4 isolation levels, transaction isolation levels. Okay, and by isolation levels, we mean that you have multiple people trying to touch the data, and if we're going to isolate them, you're going to say, well, no, we're not going to let everybody go at the same time. Everybody has to form a queue. Okay, if you go to McDonald's or you go to Dunkin' Donuts or whatever, right? Usually you have a queue, right? You usually don't allow people to just storm the go up to front of the counter, right? And everybody start yelling at the server of what is that you want, right? So we want to isolate, right, each one and give everybody a chance, right? So here's the first level isolation. The first level of isolation is no isolation, right? Everybody's allowed to do whatever they want, right? This is the equivalent of, everybody goes to Dunkin' Donuts and there are no queues, no lines whatsoever. Everybody can just storm at the front and start yelling at the server what they want, okay? And, and the server might listen to one or the other, right? And you might get served, maybe not, right? Or you might get the wrong order, right? It's just a mess, a huge mess. So read uncommitted is the no isolation level. Now, this might be okay, right? This might be totally fine, right? If if it's a database or a table where everybody's just reading data and the data is static, it's not changing over time, then you don't need isolation, right? Everybody's reading the same information, right? And nobody has to wait for anybody. It's just a read-only operation, so that's perfectly fine, right? If everybody's just reading, then you don't need any isolation, okay? So it's okay sometimes, depending on what you're doing. So read uncommitted. By read uncommitted means that literally means that somebody makes a change to a database, makes a change, but they have not yet committed. They have not yet committed the change. Remember when we did start transaction and we started changing values of those fields? Okay. Well, if we were using read uncommitted, then user 1 and user 2 would be able to see each other's work inside of the transaction, even though they had not yet committed the changes. Okay, and they run the risk that that user might roll back their changes, so the other user might be reading wrong information, right? So read uncommitted is can be dangerous, right? Or maybe not, depending on what it is that you're doing. If it's read only, then there's no danger. But if one of them is changing the data and the other one's reading those changes, then careful, read uncommitted is no good. By default, databases start off at read committed. Read committed means that anybody can only read information or data or records that have already been committed. Meaning, if there are records that have not yet been committed, so if you're in a transaction and you haven't committed yet, well, nobody's going to be able to see that. Right? Only the data that has already been committed you can look at. Okay. And this is the default behavior of databases. Databases start off with this isolation level. Beyond that, there's repeatable reads. So repeatable reads are a little more stricter. Okay, a little more stricter. Meaning, right? If I use this isolation level, I will be guaranteed that if I start a transaction and I read something and I go away and then I come back and I read again from the same record, I will be guaranteed that I will see that information, right? And the way that's achieved is that if I do a transaction and I'm reading something, the way it's implemented is that I acquire a lock, right? Meaning I lock the record, right? And I'm working with it and I'm reading. And since I have a lock, that means that if anybody comes in here, if they want to read, that's fine. They can read, right? But if they want to write, they can't. They will have to wait in the queue. This is not, wait, you can't write because I am reading. And I can't let you change it because I want to guarantee that if I come back and I see the same information, I will see the same information. Okay. So yeah, that's repeatable reads. Now, the more isolation you ask for from the database, the less concurrency you're going to have, right? So it's up to us to decide when is a good idea to do isolation levels and when not, when is it appropriate and when is it inappropriate, right? Again, trying to weigh the benefits, cost benefit, right, of using transactions. And then this, serializable. Serializable is, I'm locking something, nobody else can see it, nobody else can touch this. I'm the only one who's using it. Everybody who wants to touch this piece of information, get in a queue. Okay, if you want to read it or write it, right? I have all the locks, and nobody can touch this or besides myself, right? Meaning, it's called serializable because we want to serialize, put them in a series, one after another. All the requests that are coming for a particular record, for a particular table, we want to put them in order, right? so that when they come in, right, they're put in a queue, and then they access in the order that they reached. Okay, so we'll see each one of these, and we'll look at a couple examples for each one of these problems and how the database solves it. Right. So, for instance, let's take a look at read uncommitted data. Right. What could go wrong? What could go wrong? Right. So imagine there are two transactions, and they are allowed to read each other's uncommitted data. Okay. So here comes transaction one, and then takes the it's looking at different professors, and and transaction one wants to swap professor one from professor two, right? So kind of like I'm going to copy professor one in a temporary variable. I copy professor two. I copy them in the original professor one, and I then change professor one into professor two, right? So I'm going to swap them. Okay. So that's what transaction one is trying to do. And it needs to take several steps to do that. Yes. It needs to read the database, it needs to update the database, it needs to do logic. Yes. Now transaction two is also running concurrently at the same time. And transaction two is calculating the bonuses for the professors, depending on how many sections are they teaching. Okay. So yeah, so transaction one is trying to update two records. But what happens, right, if they're both running concurrently and you can't guarantee the order in which they are going because it's not serializable? Serializable would put them in the correct order. Right? But here with read uncommitted, everybody can do whatever they want. Right? So what happens if at the same time the transaction one is running? So transaction one, to do that, unassigns professor one from a section, because they're about to assign professor two to that section, and then assigns professor one to the other section. So what happens if I unassign professor one, and at the same time now transaction two just passes by and it adds up how many sections each professor teaching? Well, now it happens that professor one has been unassigned from a section that they would have gotten a bonus for. Right now, they're going to have a less of a bonus at the end of the year because they missed out on that particular section, right? Okay, so transaction two is reading uncommitted data, right? Where I was in the process of swapping these, right? Of changing this here and then moving that over there, but you came and read the data, that was not yet settled, right? I had not yet committed my changes, right? Because it's not permanent. I don't want this to be permanent yet. But because we are allowing to read uncommitted data, then we kind of come up with wrong information. So here's another example, and we have two transactions, and so this one is looking at a different problem, the repeatable read. Your logic might be written in such a way that they're assuming that when you read something from a database, you're assuming that is not going to change, not going to change on you. You're thinking that if you make it repeatable, you go and read it again, you're assuming, your logic might assume that nobody's touching that, it's just you, that data only belongs to you, and that might not be the case. Right? So for instance, let's take a look at two transactions. One of them, so let's assume this student has $50 in their account, and transaction one is withdrawing $10, but transaction two is depositing $1,000. Right. So transaction one, believing that they're the only ones touching this account, they read $50. Well, I'm sorry. Yeah, they read that there are $50 in the account. Says, okay, I got all right. So the student has $50, and it's deciding blah blah, and the student hasn't yet decided how much they want to withdraw. Meanwhile, transaction two comes in and deposits $1,000, right? And so what's the total amount in the students? It's $1,050, right? Because the student hasn't yet withdrawn anything, right? So now imagine that they decide that, oh, I just want 10 bucks. So the transaction one, assuming that the database still has $50, right? Because it just read 50. So it does the math. 50 minus 10, that's 40. I need to update the database to be $40. Okay. So I go back and write $40, blowing away the $1,050 that were there already. Poof, I've just lost $1,000. They're gone. Okay. Again, because the logic was assuming that we could repeatedly read the same information, that we were the only users using this, right? Now here's another example. It's called a phantom record, right? Phantom read. Imagine, at the end of the year, the student body, with the student fees, they have $100,000 they put together, and there's 1,000 students in the department, and they want to break it up into all the students. So the database makes the simple math saying, okay, $100,000, 1,000 students, everybody's going to get 100 bucks. Okay, well, what if, right? What if after making this decision or this calculation, right? The algorithm, after calculating $100,000 divided by 1,000, it's 100 bucks each. Now I'm going to go and put the $100 in everybody's account, right? Maybe your meal account or whatever, right? He's going to deposit 100 bucks so you can go and eat. I made the decision 100 bucks. What if, after calculating that's 100 bucks per student, somebody comes in and they insert 10 new students into the student body, right? Right before I had decided to go and deposit 100 bucks for every student. Well, now I'm going to be depositing $100, not to 1,000 students. I'm going to be depositing to 1,010 students, right? So all of a sudden, instead of distributing $100,000 amongst 1,000 students, I'm giving away more than $100,000. Okay, this mysterious new students are now going to get money that was not allocated for them, right? So yeah, so lots and lots of different things that could go wrong if we assume that we are the only ones manipulating the database, right? Okay, all this is to say that we need a mechanism for isolating these operations, right? So that they can work, as if they were the only ones, even though we know it's not the only. These are not the only processes running at the same time, but they need to be able to. The logic needs to be able to execute as if they were the only ones. Okay, they need to isolate them. Okay, and so the isolation is called the serializing the data. We need to serialize the data, right? We want to keep the concurrency, the efficiency of concurrency, but the consistency of serialization. Yeah, so we mentioned there are 3 different types of inconsistencies: dirty reads, non-repeatable reads, and phantom reads. And so again, these are examples of dirty reads. We did this already. So here's an example, right? So we have here 2 different transactions. Transaction 1 is ready users, right? And their age is 20. And then comes transaction 2. They update the age to be 21. Then transaction 1 reads the change and sees that it's 21, right? But notice that transaction 2 has not yet committed the change, right? So that means that if we allow transaction 1 to read the 21, we're allowing dirty read, right? Because notice transaction 2 at the end is going to roll back their change, right? And so it's going to leave the age where it used to be at first, which was 20. See that? So we might give a drink to a minor. So non-repeatable reads, right? Here's an example of a non-repeatable read. Right? I come in here, transaction 1 reads the values from user, okay, and then I get some value. Transaction 2 comes in and makes a change, and transaction one makes the same read again, but they're going to get a different value this time, right? So if their logic assumed that both select statements were going to come back with the same value, then they're going to get a non-repeatable read, right? And finally, here we are doing updating, right? And we're assuming that we are this is during read, sorry, non-repeatable read. A non-repeatable read, we are retrieving. Wait, did I copy this twice? Oh no, here it is. Here's the phantom read. Sorry. Phantom read is I'm reading multiple records, right? That users' age is between 10 and 30, and it might come back with maybe 20 folks, right? But then if I insert in somebody who meets the criteria of between 10 and 20 and 30, it turns out that I would have an additional user, right? And so this is the same thing as a dirty read, but where you have a range, have multiple records that meet the criteria as opposed to just one record. Okay, so it's a phantom read. It's like a non-repeatable read, but with multiple records, not just one record. So how do we deal with it with each one of these? How do we deal with it? We apply isolation levels. Okay, these are the 4 isolation levels, right? Read uncommitted means no isolation at all. Whereas, so read uncommitted means no isolation whatsoever. Whereas serializable is all serialized, everything's serialized, right? So they are increasingly more restrictive isolation levels, right? From no restriction all the way to full restriction. And then there are 2 in betweens, right? Read committed and repeatable reads, right? Yeah, so read uncommitted isolation is the lowest isolation. Nothing is we don't stop you from doing anything, right? You can just go ahead and do whatever you want. Dirty reads are allowed, right? You can read things that have not yet committed, right? So one transaction can see things that have not yet committed by another transaction. Obviously, this is the fastest executing, right? Because nobody has to wait for anybody, right? And I can just read the data and I'm done, right? I can get in and out real quick without talking about locks or anything. Read committed, right, is going to guarantee that you only read data that has already been committed, and this is the default. Usually, this is what databases default to, right? Read committed. So restricts readers from reading intermediate, uncommitted, dirty reads, right? And once the read is complete, then you can go back and change the data. So you cannot change data unless you have unless you're not reading it, right? Then you have let's see, read. Okay, you acquire read and write locks on the data that you're selecting, and at the end of the transaction, you release those locks so that other folks who might be waiting in the queue can come in and reacquire those locks. Right, as soon as the select statement performs, right, the locks can be reacquired. We don't lock ranges, right? Because you're accessing an individual record, right? And so we don't lock multiple records or tables, entire tables, right? So we don't lock rows 20 through 50, right? Just that individual record. But so because we don't have those locks, non-repeatable reads can still occur. Phantom reads can still occur, right? It's a little bit slower than a read uncommitted, right? But not that much slower. Then you have repeatable reads, isolation levels, right? We acquire read and write locks on the selected data. No range locks, so you can still have phantom reads, right? But it fixes non-repeatable reads for individual records, but not for ranges of records. Okay, so phantom reads can still occur. So this one is even slower than read committed. And finally, we have serializable. This is the slowest, right? Because this is locking everything, right? It's blocking everything you acquire. the data also including the range lock, right? Wherever you have a where clause, when the where clause might refer to multiple records, not only just one record. You might say, folks who are in the age between 30 and 40. Well, that means that it could be hundreds of users, right? And you acquire the locks on all 100 records, right? And anybody who's trying to touch those records, they are put in a queue. Okay, so this is definitely the slowest. And so here's a graph, right, that illustrates, the different things that could go wrong here at the top level. Right, these are the things that could go wrong, dirty reads, non-repeatable reads, and phantom reads. And then down here is listed the ways that we can fix them, right? We can say, the different isolation levels, right? And these are standard names, read uncommitted, read committed, repeatable read, and serializable. And so what this is saying is that in read uncommitted, all these three things could happen, right? It's unsafe. Dirty reads are unsafe, non-repeatable reads unsafe, phantom reads, they all can happen, right? Because there are no locks. Anybody can do whatever they want. When you apply read committed isolation level, you're fixing the dirty read inconsistency, right? But you can still have non-repeatable reads and phantom reads, right? Those are unsafe. If you turn on the repeatable read isolation level, then now the dirty reads and non-repeatable reads are fixed, but you can still have phantom reads, right? Or if you choose serializable, then that fixes everything, right? This says, right, it fixes dirty reads, non-repeatable reads, phantom reads, because it acquires all the locks that it needs to make sure that everybody sees the database consistent. Okay, transaction demo. Okay, this is the demo that we showed you on Tuesday, but using the accounts, right? Where we have a balance, right? That one transaction is going to initialize to $100, right? And depending on the transaction, right? One of them tries to update the balance by adding or depositing $50, right? And then rolling it back and canceling that change and bringing it back to whatever its original balance was, right? But if you commit, then the data shows that the change has been made permanent. Okay. Now you can by default, right, auto commit is a flag that says that each statement, each select statement, each update, each insert is its own transaction, meaning the change is made immediately, right? And that's the default. Default behavior is that when you do an insert, an update, a delete, a select, right, that statement occurs within a transaction, which starts on its own and then auto commits at the end. Right? So at the end of an insert, right, it auto commits that those changes are made permanent immediately. Okay. Well, you can turn that off. You can turn auto commit off so that now you can handle your own transaction begin transaction, rollback, commit, so that now you're responsible for doing the commits, right? Which you can start by saying start transaction. Okay, so here's an example. This is the same example that we went over earlier this week, right? Where we set. Oh well, no, this is a little bit more interesting. This is actually setting the actual isolation level, where you can set the isolation level to be serializable, repeatable read, right? Read uncommitted. You can set it explicitly, right? And you can see the changes of me trying to set the account, and then once I change the transaction and make the changes, you'll notice that nobody sees the changes until I do my commit, right? So it obviously implements read committed. Okay. Anyway, any questions? That make sense? No questions? Okay. All right, so all this is all in good, as you interact with the database yourself manually, as you as you send those commands to the tables and whatnot. But right, obviously, whenever you're going to actually implement an application, you need to be able to do this programmatically. Right? You need to be able to issue these commands not from the console, right, interacting with Workbench. You need to be able to issue these commands programmatically from whatever programming language you're going to be using. Right. So, for instance, JDBC has APIs that allow us to issue the commands of starting the transactions, committing the transaction, rolling back the transactions, right? And so JDBC by default, assumes that all the commands are auto-committed, right? So if JDBC sends a select statement or an insert statement, an update statement, right? The assumption is that all these are single executables that they're going to auto-commit and make those changes permanent immediately, okay? But we can change that, right? We can change that by asking the database to stop using auto-commit, right? And so this is just presenting that auto-commit is not enough, right? That auto-commit for more powerful, more sophisticated types of interaction, especially when we have more than one user, auto-commit is not enough, right? We need to be able to control the transaction and the isolation level programmatically, right? This goes to the same example as the two professors that we're swapping, right? And we want to, calculate their bonuses, right? So here we have a JDBC updating a command saying that I'm going to update for a particular section 43. I'm going to change it to Brando, the professor, or Einstein, right? I'm swapping them too. The two sections. So I guess Einstein is going to teach acting, and Brando is going to be teaching physics. So what happens, right? Here's where we execute the updates, right? Where we are able to execute the fact that Brando is teaching section 43. But what if the server crashes right here? The server crashes or something goes afoul, right? And we were never able to set Einstein's teaching load, right? We were able to set Brando, but not Einstein. So Einstein, if we go in and then calculate their bonuses based on their section load, right? There might be getting a lower bonus, right? Which is not right. So we need to be able to control our commits, right? So instead of using auto commit, we're going to turn it off, and that's great because JDBC has a method called set auto commit where you can either turn it on or off. Once you turn it off, though, now you're fully responsible for programmatically committing or rolling back any of these transactions, as opposed to letting the system do it for you. Okay, so you set auto commit to false, and now you have to make the changes permanent yourself, either rolling back or committing. Okay, so here's the way it would work. You would say, set auto commit to false from the database, from the JDBC driver. Do all your database work here, right? And again, none of the any inserts, any updates, any deletes that you might have done with JDBC are not made permanent until you run commit. Right? Commit, it makes the change permanent so that everybody can see it. Notice that we put the rollback here to try catch block. Kind of tell that if something goes wrong, an exception is thrown, we want to roll back our changes. Any inserts, any updates, anything that we might have done is invalidated, right? If we throw some kind of exception, right? So we want to go back to a previous stable state, right? So that we don't leave the database in an inconsistent state. So here it is. So we set auto commit to false, right? And we are meaning now we're gonna do our inserts, our updates, our selects, our read. And it's gonna happen within a particular transaction, right? And then we're gonna commit the transaction at the very end when we're done interacting with the database. Okay. Or here's a couple examples. Transactional profit sharing. This is the same profit sharing that we looked at earlier, right? That we wanted to share $100,000 among students, right? And so, but we need to calculate how many students there are. So here's select count of how many, right, students there are. So once we count that there are 100 students, right? We execute the query. There's 100 students, and comes back with 100. But what if somebody, a second thread running parallel to us, inserts 10, 100 records that were not counted originally. So now, we're going to deposit presumably $100,000 to, we're going to update everybody's meal plan, right? But now they're going to be 10 or 100 more meal plans than before, right? More than the ones we calculated here, based on the counts, on this count, right? So we might have calculated that there were 1,000 students, but now there are really 1,100 students. So when we deposit, right, and we deposit the meal plan, okay, we're going to be giving out $100 to folks who were not there before, right? We're in the part of the calculation of the count originally, right? So there it is. So we are, here's the example, right, of the transaction of updating the meal plan, okay, and then changing the balance. So here's another one, deleting rows while iterating over them. Oh, wait a minute. Execute update. Oh yeah, no, I don't. Yeah, that's a new feature of JDBC, which I'll talk a little later to advance some of the advanced features. Okay, so JDBC supports all the isolation levels that we mentioned earlier, right? The read committed, read uncommitted, repeatable reads, and serializable, right? And the way you set them up is by when you establish a connection with the database. Once you have the connection object, you can set the transaction isolation, right? There's a function on the connection, and then you can pass any number of constants that are declared as static variables of the connection class, right? So you can say, I want this transaction to be transaction serializable, meaning, right, the changes are going to happen in series, right? That we're not going to allow to read things that are uncommitted, right? Right, as I mentioned earlier, the default isolation level is read committed, which is what we demonstrated back on Tuesday, right, where we saw two users and they couldn't see each other's changes unless they committed their changes. Okay. Yeah. So here's just pointing out that you should analyze whether the transaction that you might not need anything better than read committed, right? That maybe it's not worth to go all the way up to transaction serializable. Okay. It depends, right? Again, if the table is mostly read, then you don't need any isolation level. Okay. Okay. All right, folks. That's all I had for you today. Any questions? All right, then. Thank you. Bye.
Have a good weekend.
You too. Take care.